Welcome to Study Loop.
So in this problem, we are given a blood sample which is buffered by carbonic acid and the bicarbonate ion, and we are also given the concentration of this acid and base in the normal blood plasma, and we also given the pKa value for the acid. So in the first part of the problem, we need to find out the pH of the blood plasma, which we can do very easily by just applying our Henderson-Hasselbalch equation. So let's first write down the data we are given here. So we are given the our acid concentration, which is H2 CO3. This is our acid, carbonic acid in the blood plasma, which is a concentration of 0.0012 mole, and we also given the concentration of our base bicarbonate ion, which is 0.024 m. We also given the pKa of the acid, which is 6.1. So just plugging in these values in our Henderson-Hasselbalch equation, we can find the pH. We know that pH equal to pKa plus log of base concentration over acid concentration. So this is our base concentration. We put it over the acid concentration, which is 0.0012. And by just solving this equation here, we'll have the pH of the blood plasma is 7.4. So this is the pH of blood plasma. Now in the second part of the problem, we are asked that we are given the volume of the blood in a normal adult is 5 liter, and we are asked to find out how much or what mass of hydrochloric acid can be neutralized by this buffer system, the carbonic acid bicarbonate buffer in blood, before the pH falls below 7. So in this case, what we have to do is first we have to find out um, the reaction which will take place when we add the HCl. But before doing that, we have to find out the number of moles of the carbonic acid and the bicarbonate, because we will have to calculate how much change there will be in the number of moles of acid and base after the addition of HCl. So our initial number of moles of our acid here, H2CO3, is simply the multiplication of the concentration, which is 0.012 m, and m means mole per liter, times the volume, which is 5 liter. So if we just cut the liters, and if we just multiply these two, we will have the number of moles here, and the number of moles will be 0.006. Now similarly, we will calculate the moles of our base, which is the bicarbonate ion, HCO3 minus, and it has a concentration of 0.024 mole per liter times 5 liter, and we will have a concentration of 0.12 mole. So now we have our initial number of moles of acid and base, and now when we add the HCl, we are basically adding the H plus ion. So let's set up the ionic equation for the addition of HCl, which will be H plus will be added from the HCl, and this will react with the basic part of the solution, which is HCO3 minus, and In result, we will get the carbonic acid H2CO3 aqueous. So now these are our initial number of moles of acid and base, and if we add x mole of H plus, so in the resultant solution we are actually reacting with x mole of acid. That means in the resultant solution we will have 0.006 minus x mole of acid, because the x mole of H plus will react with x mole of HCO3 minus, and that's why in the resultant solution we will have this much acid left. And so uh, not acid, this much base will be left in the, so this is the base here, so this much base will be left in the resultant solution, and here is our acid in the product side, so we are actually adding x mole to the product, so our resultant product moles will be 0.12 plus x mole. So these are our new number of moles for base and acid. Now we just plug them in our Henderson-Hasselbalch equation with the pH value. So the pH value, which is our limit in this part, is that the pH cannot fall below 7. So we set up our pH as 7. Our pKa value is 6.1 plus log of, we put the number of moles of base over the number of moles of acid. So our number of moles of base here is 0.12 minus x, and number of moles of acid here is 0.006 plus x. So if we solve this equation for x, we will have the value of x as 0.0082. So this is the mole of HCl we can add, and that can be neutralized by the buffer before the pH falling below 7. So from the number of moles we can easily find the mass of the HCl. We just multiply this by the molar mass of HCl, which is 36.461 gram per mole, and it will give us the mass as 0.3 gram. So this is the mass of HCl which can be neutralized by the buffer system of the blood before the pH fall below 7. Now in the third part, we have to find out how much or what is the mass of sodium hydroxide can be neutralized before the pH rises above 7.8. So in this case, similarly, we'll do just the exact same process. Just as we are adding base here, so if we set up the reaction, that will be, we'll have OH minus from the sodium hydroxide, plus we will have this will react with the acidic part, carbonic acid, and finally we will get bicarbonate ion from this. Now, so what we'll do is so as before, our previous or initial number of moles of this acid was 0.006, and number of moles of base was 0.12. Now if you're adding plus x moles of sodium hydroxide, that means this will react with x mole of carbonic acid, and in the resultant solution we will have 0.006 minus x mole of acid, and it will add x mole to the base. So in the resultant solution we will have 0.12 plus x mole of bicarbonate ion. So these are our resultant number of moles of acid and base. Now we just plug in these values again in the Henderson-Hasselbalch equation, and in this case our pH limit is 7.8. So 7 point, and so pH equal to pKa value here is 6.1 plus log of our number of moles of base 0.12 plus x over number of moles of acid 0.006 minus x. And again, solving this equation, we will have the value of x as 0.0035. So this is the moles of sodium hydroxide that can be neutralized by the buffer before the pH rises above 7.8, and just multiplying this number of moles by the molar mass of sodium hydroxide, which is 39.996 gram per mole, we will have the mass of sodium hydroxide as 0.14 gram. So this is the mass of sodium hydroxide that can be neutralized by the buffer system before the pH rises above 7.8.